This is Journeys to the Ice, the podcast of the Antarctic Research Centre. I'm Matthew Wood. This week on the podcast,
You're just coming out of this glacial period with all these valleys with rich alluvial soils, and then you start to warm things up. So all of these podocarp hardwood trees will colonise areas suitable for growth.
a glacial period or an ice age represents a significant disturbance to the global biosphere. On land, the rapidly warming climate characteristic of deglaciations raises the tree line, and in doing so opens up new ecological niches for plants. It may seem counterintuitive, but some of the best records of terrestrial vegetation succession at glacial-interglacial timescales are actually found at the bottom of the ocean. This is certainly true for the west coast of New Zealand's South Island, where the pollen and spores of land plants are quickly and continuously delivered by rivers from short, steep catchments to the stable sedimentary environment of the deep sea. Matt Ryan recently completed his master's research at the ARC, during which he produced one of the longest west coast paleovegetation reconstructions to date, and related this new record to concurrent local sea surface temperatures. His findings have helped explain the conspicuous present-day absence of temperate beech forest across much of central Westland. G'day Matt, welcome to the podcast. Thanks for giving us some time today.
Yeah, it's a pleasure to be on here.
So you handed in your master's thesis a couple of weeks ago, and you're currently writing up some papers and preparing to start on a PhD, is that right?
Yeah, that's correct.
Okay, so you're interested in terrestrial palynomorphs, so that's pollen and spores. Very briefly, what are these and how did you use them in your master's study?
Pollen and spores are small cellular bodies. They're produced basically as part of the reproductive cycle of plants, and they're dispersed in the environment. They have a tough outer wall, which is the exine of the grains, and it's actually made up of sporopollenin, which is really resistant to degradation. This can preserve well in both marine and terrestrial environments, which makes them really useful for paleoenvironmental reconstructions. What we wanted to try and do is use these palynomorphs and reconstruct paleovegetation for the South Island, New Zealand.
And of course, your particular focus was on central Westland. And for anyone unfamiliar with New Zealand geography, this is a pretty unique place really, with this huge annual rainfall and really steep terrain due to the uplift of the Southern Alps, which are pretty close to the coast in this region. So I guess what are some of the potential challenges with this kind of paleoclimate study where you're using terrestrial palynomorphs that are actually preserved in marine sediments well off the coast? And what is it about central Westland that makes it a really good candidate setting for this kind of study?
So for the study, we obviously used a marine core, and it was collected from an overbank deposit on the Hokitika submarine canyon system. Marine records offer an advantage in that they're continuously deposited in some areas, whereas terrestrial records can actually be eroded away and aren't often preserved in the landscape. And often terrestrial records cannot be dated past radiocarbon dating. When palynomorphs, pollen and spores are produced, they get transported into the ocean, mainly from rivers, because the west coast is against the prevailing wind direction. And also, we find a large proportion of fern spores in the study, and that indicates that a lot of the stuff has come from rivers, because fern spores are unable to be transported aerially. One thing which is important in this study is to understand the nature of different grains, how they preserved, how they dispersed, they produced in large numbers. And so when we look at any sample, it's important to understand its representativity. So are some of these grains more abundant than others? And is this the nature of the modern environment, or is something producing this artifact? The body of some of these grains has wings on them, so they're actually quite efficient for hydrodynamic transportation. So often they can be hydraulically sorted. We just wanted to really find out that these pollen and spores don't get sorted with increasing water depth. So we actually collected modern surface samples just to make sure that these weren't biased with increasing distance offshore, so we can accurately make reconstructions back through time. The west coast is also unique in that the continental shelf is quite short, whereas in other areas in New Zealand and the world, during a sea level low stand that is a glacial period, the sea level, when it drops 120 metres during these glacial periods, can actually go some distance offshore. That changes the behaviour of the catchment, so it increases the catchment area.
And as you point out in your thesis, during these glacial periods when you have the shoreline out at the edge of the continental shelf, because the shelf is so thin in this part of Westland, there's actually only a change in the area of river catchments of about 1% or so.
Yeah, that's correct. During these low stand of sea level, we can relate it back to the Hokitika catchment quite effectively. The Hokitika River is the second largest suspended sediment producing river of Westland, and palynomorphs often get transported with suspended sediment. So we can say that a lot of this stuff getting into this canyon is actually coming primarily from the Hokitika River. So we can make paleo-environmental interpretations back to the Hokitika catchment over time, whether that be an interglacial period like the last interglacial, MIS 5e, or glacial periods.
Now, you mentioned before that the core that forms the basis of this study was retrieved from an overbank deposit on the Hokitika Canyon. Could you elaborate a bit more on this sort of offshore component of the Hokitika sedimentary system?
Yes, certainly. The Hokitika Canyon complex is quite like a sinuous, meandering river. It's been mapped, I think, at least to 1,600 kilometres offshore. And so the core, which I looked at for this study, is taken on the true right bank of the Hokitika Canyon. When you have a turbidity flow which goes down the canyon, so silt and mud suspended in the water column, it's sort of a density flow going down the canyon. They preferentially deposit material on the left-hand side of the canyon due to Coriolis in the Southern Hemisphere. However, on meander bends, the material actually preferentially deposits on the outer side of the bend.
I assume that's because the flow has a momentum, so in this case, when the canyon turns to the left, the flow essentially overcomes that Coriolis force, and some of that fine material will spill over and deposit onto the true right bank.
Yes, that's right. So those fines would also contain the pollen and spores, which we have used in the study.
Now, turbidity flows are generally initiated by either big flood events or by earthquakes that remobilize material stored on the shelf. So, is there a problem at all in the fact that this sediment delivery mechanism is inherently episodic? Or are you dealing with timescales in your study where this isn't really an issue and sediment delivery is effectively continuous?
Over this 3.2 meter core, which we looked at, we've basically got a sample every 2.1 thousand years. And these events would be episodic, but palynomorphs could also be transported offshore from just material settling out of the water column from the short, steep rivers of Westland. So the time scale which we're looking at, it isn't as important.
In any study that involves a proxy record of some sort, one of the first things you obviously need to do is figure out how old the various layers in that record are. How did you go about getting age control for your core in the absence of any easily datable individual horizons, such as volcanic tephra layers, for example?
We developed an age control for this core using planktonic foraminifera, used Globigerina boloides, which is a species which lives up to 200 meters in the water column in sort of upwelling zones. So we were able to pick 3 to 4 Globigerina boloides out from depths down the core. So that was something like 97 samples. And send these to NIWA and develop an oxygen isotope curve. So this is the change in delta O18. So the variation with this, we're able to tie to other global records that are independently dated, which generates an age control. So that produced an age of 210,000 years for this core. Westland is also unique in that it has an excellent long terrestrial record of paleovegetation change from Okarito Pakahi. And that's a 150,000-year-old record in a moraine impounded peat bog, which has actually preserved it from the ice advance of the last glacial maximum. So this basically records a record of vegetation change since the penultimate glaciation. This has enabled a correlation basically over the period of time the two have in common, so over the last 150,000 years. And the records actually do look quite similar. So this has produced the longest continuous reconstruction of paleovegetation change for Westland by at least 60,000 years.
We should turn soon to some of the results from your paleovegetation study, but first, could you explain the concept of the tree line? Because I think this really helps in making sense of vegetation succession on land at glacial interglacial timescales.
The tree line exists globally at about the 10-degree isotherm. That's the temperature it needs to be around the summer months for plant growth. So let's say that the tree line is 1,200 metres in Westland currently. This is thought to have reduced up to as much as 800 metres downhill during these glacial periods.
So, referring now to your pollen record, what are some of the general plant species assemblages that would have been typical of central Westland during glacial periods and interglacial periods, respectively?
Glacial periods in the core are actually quite similar, with a higher proportion of herb and shrub pollen and a reduced amount of tall tree pollen, particularly reduced amount of podocarp hardwood pollen in comparison to interglacial periods. The herbs generally consist of grasses, poaceae, which can be found in flat alluvial plains or predominantly in the higher alpine regions, anywhere above 1,200 metres today. The herbs also contain Asteraceae, which is predominant in the core, and these can exist as shrubs in the lowland zone up into the montane zone, which is actually quite high, anywhere from 400 to 1,200 metres. During the glacial periods as well, particularly that of MIS6 and the last glaciation, there's a lot of Nothofagus taxa as a tall tree in this region because this is often more tolerant of drier, cooler conditions. During interglacial conditions, there's abundant tall tree taxa, particularly that of podocarp hardwood species. Frost and drought intolerant species are found present as well. Both in MIS5, so the last interglacial, and MIS7A, there's nastigious pollen present, which is presently not found in the Western region today. And so this suggests that MIS7A may have been similar to the present day, however becoming slightly cooler in the later period of MIS7A, with an absence of frost-intolerant taxa. The last interglacial appears to be slightly warmer than the Holocene, however, with higher levels of frost and drought-intolerant taxa in the region during this time, and that actually also agrees with sea surface temperature records, which are quite proximal to the core that we're looking at in this study. These sea surface temperature records suggest that temperatures may have been up to 3 degrees higher than the present day.
Right, so now we've discussed three different proxy record types from your study area. From your own core, there's obviously the pollen record, but there's also the delta O18 curve, which provides that reliable age control. And now there's also this sea surface temperature record from a site close to where your core was collected. Now, each of these proxy records ultimately reveals glacial interglacial cycles, but how did the records compare to each other in terms of specific timing?
So the sea surface temperature record and the podocarp hardwood species, so the ones that start to recolonize first, are actually in phase with each other. During the last interglacial, podocarp hardwood taxa starts to come in first. At the same time, we see increasing shrubs and tree ferns. However, there's a lag of about 3,000 to 4,000 years between the initial rise in sea surface temperatures and Dacrydium capresinum, which is REMU, and that comes in at a time where the isotope record shows depleted delta O18, so less ice present at that time. The REMU is actually in phase with the Northern Hemisphere ice volume effect, and that actually is quite a temperate taxa. It needs high temperatures to survive, and it needs rainfall of 2,000 millimeters per year. So if rainfall is not a limiting factor, this suggests that temperatures were higher in this region at this time.
Now, there's this really interesting present-day vegetation anomaly called the Central Westland beech-gap. What exactly is this, and how has your work helped to explain it?
The Central Westland beech-gap basically refers to a 160 kilometre disjunction of Nothofagus taxa, so the absence of southern beech forest between the Taramakawa River in North Westland and the Paringa Valley in South Westland. So Nothofagus is suitable to grow in the Central Westland region, however it doesn't. Other studies have shown that Nothofagus is thought to have existed in this region from 200,000 years to approximately 150,000 years. My study shows that during MIS7A, from 210,000 years ago, there's an abundant amount of beech forest in the Central Westland region. It shows that beech forest did persist in this region. It continues to persist during the MIS6 glacial, and then during the transition to the last interglacial, it basically gets wiped out, if you like. from the outcompeting podocarp hardwood taxa and ferns, which are really competitive due to their more efficient seed dispersal and the ability to occupy more fertile soils. And if you can imagine, you're just coming out of this glacial period with all these valleys with rich alluvial soils, and then you start to warm things up. All of these podocarp hardwood trees will colonise areas suitable for growth, which are these inland valleys, faster than the Nothofagus growth, because Nothofagus actually has a much poorer seed dispersal due to their heavier seeds.
So during your research, you were able to compare your own West Coast pollen record to a previously published pollen record from off the Canterbury coast. What, if anything, did this comparison tell you about the differences in paleovegetation between the eastern and western sides of the South Island's main divide?
I redated a long record of paleovegetation change from the east coast. This covers at least 4 glacial interglacial cycles, and it has much more abundant herb taxa than the marine record that I'm looking at in this study. This is primarily a result of the exposed continental shelf, which goes a lot further distance than on the west coast of the South Island. So it has a lot more grasses. It's a lot drier on the east coast compared to the west coast, where we still see evidence for forest.
And what about differences in terms of the vegetation response to climate change? Does one side respond quicker to changing temperatures than the other?
Yeah, so fortunately, the record, which I redated on the east coast, had a sea surface temperature reconstruction with it. And this was compared to the sea surface temperature reconstruction on the west coast. At the time when sea surface temperatures increased during the last interglacial, the west coast certainly undergoes change a lot quicker. Podocarp hardwood taxa comes in a lot quicker, whereas on the east coast this is somewhat delayed, with shrub taxa occupying this niche. By the time Rimu Dacrydium capressinum comes in on the west coast, the east coast shows tall tree growth as well, with Primnipidus and Podocarpus taxa, so tall tree taxa. This delay could be either due to temperature or precipitation, or a combination of both of these factors. So precipitation is not limiting on the west coast, however it is limiting on the east coast. As we know, you can have frequent droughts and frosts on the east coast. So the vegetation might be responding a lot quicker on the west coast because it's more of a maritime climate. So I guess the response of vegetation is driven by sort of ocean atmosphere exchange of heat over New Zealand. But also you need to consider what plants are growing in these regions as well. So are the successions the same on both sides of New Zealand?
So you're heading straight into a PhD where you'll be taking the lessons you've learnt from your masters and applying them to much longer timescales in the same general study area. You mentioned before that through your master's research, you've already produced the longest paleovegetation record for central Westland. So in your PhD, with these much longer sediment cores, you'll really be getting some pretty exciting results and doing some reasonably cutting edge science, I guess.
Yeah, it's going to be really interesting. And the fact I'm working with GNS and NIWA for this has made it a really amazing project, and how we can look at marine cores to figure out what's happening in the ocean and what's happened on land at the same time is really interesting.
Do you find that the more you learn through independent research, the more you realise just how much more work there is still to do in this area of science?
Definitely. Yeah, lots of questions still to be answered, and hope to try and tackle some of those questions for the PhD.
Well, all the best for your future research, Matt, and thanks a lot for your time today.
Thanks, Matt. It's been a pleasure.
For more Journeys to the Ice, visit sciblogs.co.nz/Journeys to the Ice.